Just a quick note before we start, you can ask your questions online by going to this website and entering this GeeCON 2013 code. And you will ask your questions there, and I guess you will also see other people's questions. And I also have 3 t-shirts for giveaway, so I will deliver them during QA part. Here is our agenda for today. We will start with a bit of talking about distributed coordination, what it is, why it is challenging, etc. Then we will walk through a couple of distributed coordination systems to see, we will walk through a couple of distributed coordination systems to see how they build their APIs for coordination tasks and how those APIs evolved over time. Then I will discuss why it makes sense to use JDK's concurrency APIs for distributed coordination. Then we will go into our solution. So just a quick poll before we start. Anyone familiar with Hazelcast, using it in production? Check the project. Yeah, okay, we have a bunch of people. So no worries, you don't need to know anything about Hazelcast for this session. So basically, it is an in-memory data structure cluster. It's an open source project written in Java. It gives you distributed versions of JDK's collections and concurrency APIs like maps, sets, queues, logs, semaphores, etc. And in our new release, which is 3.12, we introduced a new implementation of our concurrency APIs. So today we are going to take a look at these APIs, and we will run some demos to see how to use them for distributed coordination. Okay, let's start. In today's world, our applications must be always on, right? We have scalability, high availability, and reliability requirements. And because of that, we develop and run our applications in a distributed setting. We deploy web applications, microservices, distributed databases, data processing tools, messaging systems, etc. So this is how Amazon's microservices looked like 11 years ago. It's crazy, right? I cannot even imagine its current situation. So when we have such a distributed environment, coordination plays a critical role. Maybe the most prominent example of coordination is leader election. For instance, we run multiple instances of some service or some component, and we elect a leader among those instances, and the leader becomes responsible for handling incoming requests and also orchestrating the system. Or we may be running a distributed algorithm over multiple components, and they may need to use a synchronization primitive like a lock or a semaphore or a barrier to synchronize their actions while going through this algorithm. Or we may need to track which service instances are alive, which are down. So we may need to track topology of our system, or we manage and share some configuration information or metadata information like discovery data, connection parameters, application settings, task distributions, or job assignments, anything like that. And when there is a change in these information pieces, we notify all the related components and they take some action. And the thing is, these tasks involve a lot of complexity, and usually, these tasks involve a lot of complexity, and we need to deal with saddle race conditions and several failure modes, and they are usually quite easy to overlook. So if we try to implement our own solution, most probably we will end up with a quick and dirty solution. And even if we make it correct, every application will have its own custom solution, and our application logic will be intermingled with this coordination logic. So if you would leave this session with just one conclusion, maybe this is it. Do not write your own solutions for coordination tasks. It is not a good idea. Okay, then how can we deal with our coordination requirements? Of course, there is a bunch of systems that offer solutions for these problems. These systems use consensus algorithms under the hood, so they always preserve strong consistency for the underlying data. So with respect to the CAP principle, they are CP systems. And we use these systems to separate our application logic and the coordination logic. And since running consensus algorithms are expensive, we usually do not put large data sets on these systems, and we also do not place them on the critical path of our applications. So they are usually deployed as a central repository, and they serve to several applications and expose coordination primitives. So we will take a look at a couple of these systems and investigate their APIs. It all started with a paper from Google in 2006, Paxos. Paxos is a distributed log service internally used by several Google projects. It is built on top of the Paxos algorithm. It is not open source, but the paper itself is very good, and it explains a lot of stuff in detail about implementation concerns. And after Paxos, Zookeeper was developed, I guess, 2 years later, 2 years after the Paxos, 2 years after the Chubby. Zookeeper is like the open source version of Chubby. Chubby's API significantly influenced Zookeeper, but instead of Paxos, Zookeeper uses its own consensus algorithm. And after Zookeeper, etcd was developed as another distributed coordination tool. So it started in 2013. Kubernetes internally uses etcd, so it's a very powerful one actually. And etcd engineers note that the lessons learned from Zookeeper informed its design significantly, and they made a lot of improvements over Zookeeper. And again, it works on top of another consensus algorithm, Raft. So if you look at these three systems, we see that they all offer some sort of a strongly consistent key value API at the bottom. For instance, Chubby and Zookeeper offers a file system API, a Unix-like hierarchical file system API. So you can create files and directories and persist arbitrary data on them, like service information, discovery information, settings, etc. On the other hand, in order to get better performance, etcd prefers to offer a flat and ordered key value store API instead of a hierarchical system. But we can consider both of these approaches as some form of a key value store. And these systems build their high-level coordination primitives on top of their key value store API in different ways. For instance, Chubby offers locking APIs on files, so it's directly used as a distributed log service. And the paper claims that having an explicit locking API is very useful because developers are usually familiar with how to use logs, even though they may not be familiar with complexities of distributed systems. On the other hand, Zookeeper doesn't offer any high-level coordination primitive, so it defines itself as a generic coordination kernel, and it defines receipts. So receipts are descriptions to implement high-level primitives on top of its file system API. So here's a very basic distributed locking receipt for Zookeeper to show you the idea. So suppose that we have multiple components or multiple processes trying to acquire a lock. So in the first step, they all try to create a file with the same name, and only one of them will succeed at this step, and it will be owner of the lock. So it will enter to the critical section. And all other processes will fail at this step, and they will register a watch on this file. So a watch is a basic notification mechanism in Zookeeper with some guarantees. And once this lock is released by deleting this file, all of these waiting watches will be notified, and those processes will go back to the first step to retry the lock acquire. So this looks quite flexible, right? This approach quite makes sense, because once we have a strongly consistent file system, at the bottom, we can build many coordination primitives on top of it. But the thing is, coordination primitives usually require non-trivial algorithms. So we need to make sure that we implement the algorithm exactly as described as in its receipt, or we need to make sure that we handle all the failures correctly. And this is not a trivial task. And this approach also brings a lot of burden to application developers. Because of that, a client library was developed for Zookeeper called Curator. So this library implements common Zookeeper receipts behind custom Java interfaces to hide all of that complexity. And it seems that etcd also learned from this lesson, and it started to deliver its own implementations of leader election and distributed locking primitives on top of its key value store API. So it goes without saying that all of these systems are very successful, and they empower many mission-critical software projects. But I think their approach is suboptimal in terms of their API, because they all offer some sort of a key value store API, and this API seems to me a low-level API. So it is easy to misuse, and it is not suitable for all coordination tasks, because we still need to build our own primitives on top of it to implement our scenarios. So because of that, I think we should need high-level APIs that will hide all of these complexities and also minimize all the guesswork and development effort for us. So if we look at JDK, we already have a good set of concurrency APIs for a long time, right? Under the java.util concurrent package, we have lux, we have semaphore, countdown latch, atomic classes, and many other concurrency primitives. And we use these primitives to deal with concurrency and non-determinism while we are developing multi-threaded applications in the JDK ecosystem. And if we compare multi-threaded and distributed applications, we see that these two challenges exist in both of them, right? We can run our threads in the same process or in different processes. In both cases, we have concurrency and non-determinism. And in distributed applications, there is also another challenge that does not exist in multi-threaded applications, that is partial failures. So a distributed application is expected to keep running while some of its components have failed, and in different ways, of course. So our idea is we can capitalize on this conceptual similarity between multi-threaded and distributed applications to make JDK's concurrency primitives useful for coordination tasks, and this is exactly what we did. So we already had implementations of these APIs in our previous releases, but they were built on top of asynchronous replication, and they were not offering the strong consistency guarantee, which is usually expected from such APIs. So what we did is, in our new release, we clarified and extended the semantics of these java.util concurrent APIs for distributed execution and failures, and implemented them on top of the Raft consensus algorithm. So in this work, we learned some lessons and borrowed some ideas from all other tools we discussed here, but we followed a different approach. So we present an opinionated solution. So if you want to implement your coordination use cases, you don't have to work with low-level APIs like files and directories. Instead, you can use high-level APIs that are already familiar to you from your Java development experience. So as of now, we have implementations of atomic distributed and linearizable implementations of atomic long, atomic reference, countdown latch, semaphore and log primitives of JDK, and we are working on extending this list. For instance, atomic reference can be used for sharing or managing some configuration information or metadata information between different components of your system. Countdown latch can be used as a barrier, a distributed barrier. Semaphore can be used as a synchronization primitive between different processes if they are going through some distributed algorithm. And fence lock is our new distributed lock implementation. It extends JDK's lock interface, so it works like a Java lock, but in a distributed setting. And we also, as I said, we also clarified failure semantics, clarified and documented failure semantics of these solutions or of these primitives. For instance, thanks to the Raft consensus algorithm, working under the hood, they preserve strong consistency in case of network partitions, so they are not vulnerable to split brain problems. So if your cluster splits into two groups, you will be able to use these primitives only on one side of the network partition, and by this way, we prevent their data copies to diverge from each other. But it is not only about network partitions, of course. We also documented how they behave in several failure modes. Like, for instance, what if a client crashes while it is using one of these primitives, or what if replicas of these primitives go down and up, or what if an operation is internally retried because of some failure. So we documented all these kind of failure modes. And this solution is tested with Jepsen, so we wrote our own Jepsen test suite, and I can say that our testing process greatly helped us to improve reliability of this solution. So we discovered and fixed many bugs with our Jepsen tests. As I said, we built this solution on top of the Raft algorithm. Besides Raft, there is also the Paxos algorithm, and I guess Paxos is around for 30 years, and it also has many variations. But Paxos is infamous for being a bit difficult to understand and also not covering implementation concerns. On the other hand, the Raft algorithm was developed recently with the main goal of understandability, And I think its widespread adaptation proves that it achieves this goal. It's being used by many tools, many systems. So it's a consensus algorithm, and it preserves strong consistency for the underlying data. And it can tolerate network failures, crash failures, timing failures, etc. And it remains available as long as majority of the servers are alive. So we usually run these systems with an odd number of servers, like 3, 5, 7. So 3 servers can tolerate failure of 1, 5 servers can tolerate failure of 2, and so on. So if you lose, for instance, 2 servers out of 3, it means you will lose availability, and you need to recover one of those services back in order to recover the availability. So it achieves, or it preserves, strong consistency for the underlying data, but besides that, Raft also covers runtime concerns and performance optimizations. So it offers a solution for instance, how to change membership of the consensus group at runtime, or how to apply, or how to speed up read operations by applying some optimizations, how to improve your throughput by batching your operations, etc. And in fact, these concerns are also solved in the Paxos domain, but their solutions are mostly spread around several papers and reports, etc. And the good thing about Raft is it gives you a single compact solution that solves both the fundamental consensus problem and also deals with these runtime concerns. So the Raft algorithm implements a technique called replicated state machines. So in this technique, each server keeps a log of operations and also a state machine. In our solution, our state machine is distributed implementations of the concurrency APIs. And the Raft algorithm first elects a leader among the servers, or which we call nodes. So it elects a leader between nodes, and the leader becomes responsible for handling incoming requests and replicating them to followers. And if the leader fails, a new leader is elected safely, and the algorithm guarantees that there will be a single leader that is committing operations at a time, and all nodes will commit and run these operations in the same order, incoming operations in the same order, and by this way they will end up with the same state. So we present this solution in a new module of Hazelcast. So this part is a bit related to Hazelcast. So developers usually run large Hazelcast clusters to store hundreds of gigabytes of data, but the current implementation of these concurrency APIs have quite small memory footprints. So even if you run a 100 server Hazelcast cluster, you don't have to run this solution on all of them, on all members. So instead, you can run them on just a few members of your big cluster, and we call them CP members. And these data structures live together with the other data structures of Hazelcast IMDG. And since we need to keep majority of our CP members up and running, we also implemented dynamic clustering. So it means that, for instance, you are running a cluster and a CP member crashes. So you can remove it from the cluster either programmatically or via our REST API, and you can replace it with another member to preserve your availability. And last, we also have a notion of CP groups. Each CP group runs the Raft consensus algorithm independently. So it means that if you want to improve throughput of your system, you can distribute your concurrency primitives to different CP groups, and you can also run those CP groups on different members. So each CP group will run the Raft consensus algorithm on its own, and they will not collide with each other in terms of throughput. So okay, we pretty much covered the basics. Now I will walk through a couple of demos to see how these primitives are used in action. So we will walk through a couple of demos, and in the first part we will mimic a configuration management use case. So here we are running 3 Hazelcast servers, and we will use it as a central coordination repository, and we will connect to this central cluster from our clients with different roles. So in the original version of this demo, I implemented a coordination management use case. So I had a configuration manager process, which is updating configuration of the system, and also some other services which are listening to those configurations. But that demo was a bit difficult to track, so I tried to simplify it by implementing another version of the same idea. So this time I don't have a configuration manager process. Instead of that, I have a process that I called pet owner. So it is publishing photos of its pets. And I also have a web application, which is listening to those photo changes and displaying them on a UI. And you can find this demo and the other demos I will run in my repository. So you can just clone the repository and run them on your computer. Okay, let's start. So this is our Maven POM file to run this demo. It's a very basic multi-module Maven file. There's nothing fancy about it actually. So I added my Hazelcast dependencies, Hazelcast jars to my dependency list. And this is my YAML configuration file to start my cluster. So this solution works on top of existing utilities of Hazelcast. So here I'm configuring my servers to discover each other via well-known IP port pairs. But you can also use other discovery mechanisms, for instance, cloud discovery mechanisms, etc. And here we are also enabling this CP subsystem solution by specifying that we will run 3 servers. And this is enough to run this system, but I'm also providing 2 other configuration parameters here for this demo. Let's ignore it for now, and we will talk about them later. And this is my configuration file to start my clients. So I will use these clients to connect to this server and do some actions on these primitives. So basically, I'm providing my IP port pairs of the servers, but normally you don't have to provide all of the IPs. You can also provide just one of them, and the client will discover all other servers. And this is our class to start a server instance, or we call it a member. So this is where we are starting a member. So I'm basically initializing my config object from the YAML. Then I will start my instance here. Then I'm just printing a isReady log. So that's all. And this is our domain class here. So I'm using this photo class to publish new photos of my pets. So it has an ID field that is incremented each time when I publish a new photo, and it also has a file name field. And we also have a fence field here, but let's ignore it for now. We will talk about this later on. And this is our class to publish our photos. So as I said, I'm using our Hazelcast client to connect to this coordination cluster, and I will fetch 2 concurrency primitives from this CP subsystem module. So I'm fetching an atomic reference and the countdown latch primitive, and this is what I'm doing. So first I'm creating a new photo by selecting a random photo from my random photos, and I'm putting this photo into this atomic reference field. So now I published this photo, and it can be queried by any other component that runs or that connects to this cluster. So it will be accessible from my web application. But in order to notify my web application, I'm using the countdown latch here. So what I'm doing is I'm calling the countdown method. So here it is. And my web application will be awaiting on this latch. And once I call this countdown method, it will be notified, and it will notice that, okay, now there's a new photo. So it will read the value from this atomic reference. So let's see the other side of the demo. So this is our web application. It's a very basic Spring Boot application. Nothing fancy about it actually. And this is our service class. So again, we are using a client, Hazelcast client, to connect to this cluster, and we are starting a background thread here. And in this background thread, I'm doing the reverse of what our other process is doing. So first, I will await on this countdown latch with a timeout. So this is a blocking call, and it will return either when the 5 seconds pass, or our pet owner process notifies this latch by calling the countdown method. And after that, okay, I understand that now there's a new photo. I just read it and put it into a local field in order to cache it. So when we query the last published pet photo, this service will serve it from the local field. Okay, let's see it on the console. So I've already started my cluster to save up some time, and here it is. So here is our Raft logs. So we started 3 servers, and they initialized the default CP group. So in this demo, I didn't specify any custom CP group name. So I'm running everything in the default group. So it is like the default namespace. And as you see, they initialized the Raft algorithm and elected their leader. So now here is our leader. So this is the third node, and it became the leader of this Raft group. And I'm not running any pet owner process yet, so that's why we are seeing this log. So let's start our process. Okay, let's make it publish cat photos, and we will see it here in a second, and also in the browser. So my client started, and as you see, it also discovered my servers, and it started publishing new photos immediately. So here blue lines are printed by the pet owner process, and the brown lines are printed by the web application. So as you see, when I publish a new photo, it is immediately fetched by the web application. So we can see it here in our browser. So every 2 to 3 seconds, we are publishing a new photo, and it is appearing here. So this was the first part of the demo. So here basically we used 2 primitives to implement this, metadata management use case. So we used we used the atomic reference to share some information between different components in our system, and we also used the countdown latch as a notification mechanism. So let's go back to our slides for now. So this was the first part of the demo, and before going into the second part of the demo, let's talk about FanceLock. FanceLock is our new distributed lock implementation. It is linearizable, and it implements JDK's lock interface, and it is suitable for both fine-grained and coarse-grained locking. So fine-grained locking means that, for instance, I'm running some distributed algorithm. So I acquire the lock, do some work, and release it, and I repeat this process from multiple, I repeat these steps from multiple processes again and again. So maybe our distributed algorithm has some critical sections, and we are going through these critical sections by, doing this fine-grained locking. Coarse-grained locking means that I acquire the lock and I keep it for a long time. Maybe I can keep the lock for days, weeks, maybe months. So leader election is an example of coarse-grained locking. So we elect the leader, among some processes, and it stays there until it fails, right? Or we shut it down. So we don't switch between leaders frequently. So this is coarse-grained locking, and FanceLock is suitable for both use cases. So the FanceLock solution works on top of the Raft consensus algorithm, and the Raft algorithm ensures safety of its internal state. But if we talk about distributed locking, our only concern is not the safety of the lock state. We have another critical participant in distributed locking scenarios, which are our clients. For instance, it can happen that a client can acquire the lock, then it can crash without releasing it. So in this case, if we do not perform some cleanup mechanism automatically and eventually, it means that our entire application will suffer from this problem, and the lock will be unavailable forever, right? So in order to deal with failures of clients, we introduced a session tracking mechanism to track their liveness. So what happens is, when a client makes its very first lock request, it creates a new session on the underlying CP group. Then all lock requests of this client are associated with that session. And if we do not receive any session heartbeat for some time, we assume that, so we call this duration session time to live duration or session timeout duration. We assume that owner of that session is crashed, and we close that session and we release all the locks associated with that session. And after you initiate a session in the CP group, you can, your client can be busy with doing some other work, and in the meantime, we periodically commit session heartbeats in the background to keep this session alive, and all of these session tracking mechanism and keep alive mechanism runs in the background. So you just keep using the FanceLock for for your use case, so you don't have to deal with this session stuff on your own. And this logic also works for both FanceLock and also the semaphore. So if you acquire a permit from a semaphore, this session mechanism is triggered just like the FanceLock. So we had a drawback in the first part of our demo. that we were running just a single instance of our pet owner process, and it's a single point of failure for us. So here I crashed it, and if we check the UI, there is no new photo popping up, right? So if it is a stateless process, maybe you can easily restart it, but it is likely that it can be a stateful process, or it can have a long and heavyweight bootstrapping procedure. So if we want to eliminate this drawback in such a use case, we can run multiple instances of this process, and we can make a leader election among them. So if the leader fails, we will fail over to another running instance, and we are mimicking this part in the second demo. So I will run multiple instances of my pet owner class, and I will use a fence log to make a leader election among them. So let's see it. Okay. So this is the second version of my pet owner code. So I will run multiple instances of this class. So here we are using the same primitives, same atomic reference and countdown edge primitive, and in addition to them, we are also using fence log here. So first, we are acquiring the log before starting to publish new photos. So first, multiple processes make this log call, and only one of them will succeed, and it will be the leader, and the other process will be awaiting on this log call, or it will be blocked on this log call. Either we release the log, because it is how Java logs work, right? We could also use the try log method here, but I just preferred this approach. It is simpler. So after I acquire the log in one of these processes, it means that I am the leader, and after that I start publishing new photos, just as before. So let's see this. So I'm running the second version of my pet owner code. So let's make it publish dog photos this time, and I'm starting the other one. Okay, our first process already acquired the log, so it printed this line before it made the log call, and after that, as you see, its session is created on the server or on the CP group, and after that it received the log. Now it is the leader, and as you see, it started publishing new photos. And if we check the other process, it must be somewhere. Okay, it is here. So as you see, this is the last log line printed by the second process. So currently it is blocked on the log call, and its session is also created in the background. So if we check the browser, we will see some dog photos coming up. So in this demo, we use the fence log to make a leader election over multiple processes, and here I configured my session timeout to 15 seconds. So that was the configuration I skipped in the YAML file. So it means that if I terminate the current leader, after 15 seconds, its session will be closed and the log will be released, and then it will be assigned to the other process. So if we check it here, the next photo will be a cat. So let's wait for a couple of seconds. So here it is. So after 15 seconds, the system closed our session and assigned the log to the other process. So in this demo, we relied on our session semantics to recover the log after its current owner fails. And as I said, I configured my session timeout to 15 seconds, but normally it's a very aggressive configuration for production usage, because it can happen that a client can encounter a long garbage collection pause, or it can temporarily disconnect from the cluster. And if such a failure occurs, and if we release or if we close its session automatically, it means that if it comes back alive, it can still consider itself as the owner of this log, and in such a case we will have multiple processes thinking that they are the leader. And actually we can mimic it here, because I didn't crash the previous leader, I just freezed its process and I will resume it back. So if we check our UI here, we are seeing that photos are alternating between cats and dogs. So now we have two processes thinking that they are the leader, and this is not a pleasant situation for us, because we want to avoid this situation in the first place, right? We are trying to do a leader election among them. So, okay, let's stop them first. So if you want to avoid this situation, maybe we can use a longer session timeout or maybe an infinite session timeout. By the way, default session timeout in Hazelcast is longer, it's 5 minutes. But even if, for instance, we can use a 1-hour session timeout, in such a case, we can probably have liveness issues. So let's say that we are using 1 hour or 4 hours maybe. So if it means that a client crashes, and after that we will wait for a long time until we decide to close that session and release the lock, right? So we also have a manual API to manage these sessions programmatically, but we are talking about the automatic mechanisms in this part. So if you choose a small session timeout, you are likely to have a safety problem like this one we demonstrated in the second part. And if you choose a long timeout, you are likely to have a liveness problem. And we cannot do better than this because this session mechanism offers a trade-off between safety and liveness properties. And it always boils down to the fact that we cannot make 100% reliable timing assumptions in our distributed systems, right? There is always some point that will break these timing assumptions. But we offer another mechanism to deal with these situations without sacrificing liveness. So what you can do is, what we do is we order lock owners by assigning them monotonic fencing tokens. So each fencing token is a number, a monotonic integer, and each fence lock contains a fencing token. Then we increment this token every time the lock moves from the free state to the held state or the lock state. So I'm a client and I acquire the lock, and it gives me a fencing token. So it gives me a number. And now I'm in the critical section, and I pass this token to the external services I'm communicating with in order to invalidate requests of previous lock owners. So we named our solution fence lock after the terminology Martin Kleppmann used in his How to Do Distributed Locking blog post, and we also published our own blog post to explain all this stuff in detail. So let's see it in a demo. It will be much easier to follow. Okay. So this is the last version of my pet owner code base. So again, we are using the fence lock to make a leader election here, but this time we are acquiring the lock with another method. So I am calling the lock and get fence method. So once I get the lock, I also receive this fencing token. Then I am passing this token to the photos I'm publishing. So this is where we are using this fence field. So here, when I publish a new photo, I put my fencing token into this photo. Then after publishing, I check if the last published photo contains a token that is bigger than my own token. If this is the case, it means that somehow I lost ownership of this lock. My session was closed, and now there is a new leader. So when I detect this situation, I just step back by terminating myself. So let's see this. Okay, so I will run the last version of this demo. So let's make it publish dog photos again, and let's run it here as well. Okay. So now we have a new leader. So our dog owner process is the leader, and as you see, it is publishing new photos, and its fencing token is also printed here. So it's 2514. And just keep this number in mind, and I will just freeze the process of the current leader, and in a second we will get a new leader, and it will also print its fencing token, so it will be larger than 2514. So here it is. Now we have a new leader, and as you see, it received a larger fencing token. Now I will just resume the process of the previous leader, and as you see, it terminated itself immediately, and we can verify this from the last log line it printed before killing itself. So it says, here it says that my fencing token was 2514 and the current fencing token is 2535. So now somehow I'm no longer the leader and I'm going away. Okay, so that's all for the demo part. So to recap what we have discussed and what we run through the demos, I can say that distributed coordination tasks involve a lot of complexity, and it is usually better to avoid writing our custom implementations. And the evolution of coordination systems proves that having a low-level API is not the optimal solution. Still, we need to deal with several failure scenarios and edge cases, etc. So it would be much better if we implement high-level APIs that will minimize guesswork and development effort for us, and hide all of these complexities behind fundamental and simple simple APIs. And I think we managed to handle this part by implementing new linearizable distributed versions of the java.util.concurrent APIs, the APIs that exist in JDK. And in this talk, I mostly focused on the API part in my demos, so I didn't run any demo about changing membership of the cluster or scaling the workload. But since we run these systems with consensus algorithms, we need to keep our majority of servers up and running, and handling failures and scaling the workload becomes quite critical, in such use cases. So that's why we implemented dynamic clustering and horizontal scalability features from day one. And we are working on extending our API. So we are working on a new key value store API to extend the use cases, and we are also working an event mechanism. And once we have these two features, for instance, in this demo, we will be able to use a key value store API, and we will not write our own domain class like our photo class, so it will be easier and simpler. And we are also working on disk persistence, so the current solution works in memory just like the rest of Hazelcast IMDG, but once we have disk persistence, it will be a lot more reliable. And we are also working on our tooling. So currently you can manage it either programmatically or via REST API, but Hazelcast also offers a tool which we called Management Center. So it's a web tool to manage and monitor Hazelcast clusters, and we are integrating it. We are integrating with this new solution. And last, we are also working on a command line interface, so you will be able to try this by just downloading the command line interface and trying the APIs without writing any code. So this is my resources. So if you want to run these demos on your computer, you can just clone them from my repository. And if you want to learn more about this, you can check our code samples and documentation. And if you want to try it, of course, this is an open source project. Just add Hazelcast jar file to your class path or add it to your Maven POM file, and it's good to go. So thank you for attending to my session. This is the second time I'm visiting GeeCON, and I'm really happy about it. So I hope you enjoyed this session, and now I guess we are going to go through the questions. And I have 3 t-shirts to give away. Okay. Right, sorry. So we have just a single question. So I couldn't really understand the question here. Could you please clarify? I don't know who asked this question, but so it says that why did you choose to implement thread designed APIs instead of CRED? So we implement the distributed versions of the concurrency APIs that exist in Java, and they normally used in the multi-thread applications, but multi-thread and distributed applications have a lot of similarity. So we think that they are also quite useful in a distributed execution or in a distributed environment. So that's why we implemented this solution. But I'm not sure if this answers the question asked here. So any other question?
Yes, there's one more. Yeah.
Yeah. Just as I said, we are working on a key value store API, and we will also extend these existing APIs by adding some useful utility methods. So we are working on this part as well. So this guy definitely deserves a t-shirt. Just find me. I guess we are done, right?
Yeah.
Okay, thank you.